Imagine the sudden sensation of every object around you doubling in mass. A person weighing 70 kilograms would instantaneously feel like 140 kilograms, rendering even the simplest movements incredibly strenuous. Our skeletons, optimized for existing gravitational loads, would experience immense compression, potentially leading to immediate microfractures and a complete redefinition of human mobility. Existing architecture, designed with specific material stress tolerances, would buckle under its own dramatically amplified weight, causing taller structures like skyscrapers to twist and collapse rapidly. Bridges and overpasses, engineered to distribute forces, would sag severely or snap as their support structures are overwhelmed. The ground itself would encounter unprecedented pressure, leading to localized subsidence in areas with softer soil and initiating widespread infrastructure damage. Water, while remaining fluid, would exert twice the hydrostatic pressure at any given depth, effectively making all bodies of water shallower relative to their volume and creating intensely powerful, denser currents. Even the atmosphere would compress significantly, becoming denser and much thinner at higher altitudes, altering pressure systems and potentially making breathing more laborious at sea level. The Earth itself is not immune. Twice the gravitational pull significantly increases the pressure on its core, intensifying internal heat generation. This increased compression would supercharge convection currents within the mantle, leading to a much more dynamic and turbulent interior. Tectonic plate movement would become profoundly erratic and violent, triggering far more frequent and powerful earthquakes that could reshape continents within decades, alongside a dramatic surge in volcanic activity. The planet's rotational speed could visibly alter due to changes in its moment of inertia and internal mass redistribution, subtly affecting day length and global climate patterns. Oceans would recede from current coastlines, becoming vastly deeper in their basins, while the immense pressure on the seabed might trigger underwater fault lines and generate tsunamis of unprecedented scale and force. The magnetic field generated by the outer core's motion might become significantly stronger or more unstable under these new internal dynamics, with direct implications for atmospheric protection and satellite functionality. With a denser atmosphere, global weather patterns would shift dramatically, featuring more intense storms driven by concentrated air masses and altered temperature gradients. Even the crust itself would undergo constant subtle deformations, like a massive slow-motion accordion, leading to ongoing landscape transformation. Terrestrial flora would face an immediate and existential crisis. Tall trees, no longer able to support their own dramatically increased weight, would inevitably snap and fall, leaving behind a landscape dominated by low-lying, sprawling, and extremely robust vegetation. Large animals would struggle immensely to move or even stand, leading to a rapid decline and eventual extinction of most existing megafauna, favoring much smaller, squatter, and heavily built forms of life. Flight for nearly all insects and birds would become physically impossible, as the necessary wing strength and air density for lift would be prohibitively high, effectively grounding most aerial species. Human physiology would undergo profound and immediate stress, with the cardiovascular system working relentlessly to pump blood against the doubled gravitational pull, leading to rapid fatigue, dizziness, and potential organ failure as tissues struggle for adequate circulation. Bone density would increase dramatically in surviving populations, not only for structural support, but also as a means to cope with the added stress, making skeletal structures much more robust. Over many generations, the evolutionary pressures would likely lead to humans with significantly shorter, wider statures, powerful, denser muscles, and perhaps even modified internal organ placements, optimizing their structure for survival. Even the distribution of nutrients in the soil would be altered, as gravity pulls water and dissolved minerals much deeper and faster, changing soil composition and profoundly affecting plant growth patterns and crop viability. The Moon's orbit around Earth, entirely governed by gravity, would be profoundly altered. With Earth's doubled gravitational pull, the Moon's stable trajectory would destabilize, causing it to spiral inward towards our planet at an alarmingly accelerated rate, potentially leading to a collision in geological terms. Tidal forces on Earth, already a significant factor in coastal dynamics, would become exponentially stronger, leading to catastrophic high and low tides that would reshape coastlines daily and devastate marine ecosystems. The Sun's gravitational influence on Earth would remain constant, but our planet's increased mass would significantly enhance its own gravitational lensing effect on distant starlight, making astronomical observations near Earth more complex, yet potentially revealing new phenomena. Over vast geological timescales, the increased internal stress and mass could even subtly influence Earth's precession and obliquity, causing its axis of rotation to shift and thus dramatically altering global climate zones. The increased gravitational field would drastically raise the escape velocity required for space travel, making it far more fuel-intensive and exponentially challenging to leave Earth's atmosphere for orbital missions or beyond. The very fabric of space-time around Earth would curve more intensely, creating a deeper and sharper gravitational well that fundamentally alters the local geometry of the universe. This amplified curvature would even subtly affect the passage of time in Earth's immediate vicinity, accelerating the effects of gravitational time dilation.